In this video, I'm going to introduce the PTP state machine. Okay, this is how the PTP state machine looks like according to the IEEE 1588 standard. Before I describe the basics of it, let's first clarify where it is executed. If we have a network made up of boundary clocks and ordinary clocks that are interconnected by means of ports, then each port executes a copy of the state machine. This means that we have a copy of the state machine executing in this port, another one in this port, yet another one in this port, and so forth. Having clarified this, let's take another look at the state machine. Okay, it still looks complex. So what I'll do is I'll describe a simplified version of it. Basically, the state machine has a master state and a slave state, neither of which is the initial state. The initial state instead is another state called the listening state. Although there are more states, such as the passive state discussed in a previous video, these three states on the screen right now are the only ones we will discuss in this video. Considering then only these three states, let's now look at how the state machine operates. At startup, a port finds itself in the listening state. So if we have a clock that has just been initialized and that clock has a port attached to a network segment to which other PTP ports are attached, the port starts by listening. And what is it listening for? Well, obviously it is listening for messages from the other ports, but not for any old message. No, what it is waiting for is for a so-called sync message, which is a periodic PTP message that is only transmitted by PTP master ports. Moreover, a sync message is not forwarded by boundary clocks. This means that our port can only receive sync messages transmitted on the network segment it is attached to. In other words, it can only receive sync messages from this port or this one. As a result, by listening for sync messages, our port is basically checking if there is already a port in the master state in the network segment to which our port is attached. Now, our port will not wait for sync messages forever. At most, it will wait for an interval of time known as the PTP sync receive timeout. There are then two possibilities. Either our port received a sync message before the timeout, or it did not receive a sync message before the timeout. If it did not receive a sync message, our port will conclude that there is no master currently in our network segment. It will therefore decide itself to become the master. Being the master of its network segment, it will now start to periodically transmit sync messages. The period of these transmissions is called the sync interval. Now that our port has become the master, let's assume that this other port here now boots up. As the other port previously, it will start in the listening state. However, in contrast to the previous port, and since we are not considering error scenarios yet, this new port will receive a sync message. The new port will therefore know that there is already a master on the network segment. The next thing that happens is that the new clock compares itself with the current master. For this, it uses information that is conveyed in the periodic sync messages. For instance, it might check whether it has a higher quality oscillator. The exact details of the comparison are not so important for the current explanation. The point is that there are again two options. Either the new port belongs to a better clock, or it does not. If the new port does not belong to a better clock, then it transitions to the slave state. In contrast, if it belongs to a better clock, then it would have transitioned to the master state. The old master, in turn, which was already in the master state, would have started receiving sync messages from the new master, determined that its own clock is worse, and would have transitioned to the slave state. So what we have is that the new port has become the master of the network segment, while the old port has become a slave of the new master. Now, to finish up our simplified PTP state machine, there's one more transition, namely a transition from the slave state to the master state. You might ask yourself why this transition is necessary if a port can only be in the slave state if it had detected another master. Let's assume that this port here is also in the slave state. So we have two slaves, this one and this one, listening to the sync messages of the current master. At this point everything is working fine. The two slaves are receiving sync messages from the master and using them to synchronize their clocks. But now imagine that the master crashes. So it no longer transmits any sync messages. The slaves would detect this after the PTP sync receive timeout and decide that they need to become masters now. So they would both start to transmit sync messages now. These sync messages would convey information about the quality of the respective clock, and thus one port would detect that it belongs to a better clock, while the other port would detect that it belongs to a worse clock. The latter would stop transmitting sync messages and become a slave, while the other would remain as the master. In this way, the crash of the previous master was tolerated by having all slaves transition from the slave state to the master state, and then decide among themselves who remains as the ultimate master. This is then basically a rough sketch of how the PTP state machine works if we are only considering the listening state, the master state, and the slave state. The actual PTP state machine is obviously much more complex. For one, it has several additional states, such as the passive state, uncalibrated state, pre-master state, disabled state, and a few more. And second, it has a couple of more transitions.